Okay, so today we're going to start talking about meta reinforcement learning. We'll have 3 lectures on this topic, and this will be the first one that covers the basics. Okay, so for today, we're going to start talking about meta reinforcement learning. We're going to cover the problem statement. We're going to talk about how black box methods and optimization-based methods can be translated to a meta RL setting. I think that a lot of the content in this lecture is fairly straightforward. It's mostly a matter of basically taking the concepts that we were thinking about before in meta learning and trying to translate them to a reinforcement learning setting. And so we'll cover also a lot of really kind of examples of what this looks like. Black box meta RL methods are going to come up in homework 4. You'll basically get an opportunity to play around with these methods and get a sense for how they work. But the primary part of homework 4 is actually going to be on learning to explore, which is what we're going to be covering in lecture on Monday next week. And the goals of this lecture is to provide an understanding of the meta RL problem statement and a setup to help you understand the basics of black box meta RL methods and the basics and some of the challenges that come up with optimization-based meta RL algorithms. Cool, so let's get started with the problem statement. And for this, we'll recap briefly some of the things that we covered in the previous lectures to build up to the problem statement. So in the past few lectures, we've introduced model-free and model-based reinforcement learning methods, and we introduced them within this kind of general framework of a reinforcement learning algorithm that iterates between generating samples, fitting some model to estimate the return, and using that to improve the policy. For this box right here, there's a few different ways that you can estimate the return. One is to use Monte Carlo rollouts of the policy. One is to fit a model that predicts the cumulative returns. And a third is to fit a model of the dynamics, of the one-step dynamics, which can also give you an estimate of the return if you accumulate the rollouts using this one-step model. And then once you have one of these returns, you can either, one of these estimates of the return, you can either use it to directly improve the policy, use it to compute the policy with regard to your current Q function in a Q-learning approach, or optimize a policy by, for example, backpropagating gradients from a model into the policy. So these are kind of a general class of reinforcement learning approaches. Beyond reinforcement learning, back in the supervised learning setting, we also talked about these different problem settings: multitask learning problem setting, a transfer learning problem setting, and the meta learning problem. One key aspect of all these settings is that we assume that the tasks must share some structure. And kind of the key idea of meta reinforcement learning, of what we'll talk about today, is basically taking this meta learning problem, and instead of using supervised learning tasks, each of the tasks will be reinforcement learning tasks. So a reinforcement learning task, as we defined it before, basically corresponds to a Markov decision process, where tasks may vary in terms of different elements of that Markov decision process, especially the dynamics or the reward. And so what we'll talk about today is that meta reinforcement learning will basically just correspond to meta learning, where each of your tasks are these MDPs. So your goal will be, you're given some set of training tasks or some set of training MDPs, and then your goal will be to quickly learn to solve a new MDP based on your previous experience with those other MDPs. Okay, so that's kind of the high-level overview. Another view that we gave on the meta learning problem was one of basically mapping from a training data set and a test input to a corresponding prediction for that test input. So some sort of kind of function or procedure that takes in the training set, takes as input the test input, and makes a prediction based on what it learned from the training set. And the way that this is learned is through a data set of data sets. With this view, we can kind of translate this view towards the meta reinforcement learning problem statement by basically replacing supervised learning with reinforcement learning and then translating that to the meta-learning setting. So in particular, in reinforcement learning, our goal is not to map from X to Y, it's to map from states to actions. And the way that we do this is not through input-output pairs, but experience that has corresponding rewards that indicate what kinds of actions and states are good and what kinds of states and actions are bad. Now, to translate this to the setting where we want to learn many tasks and ultimately learn a new task quickly, we can kind of raise it up a level like we did with supervised learning. In this case, our goal will be, given a small amount of experience from a new task, can we learn a policy from that experience? So given a small amount of experience and the current state, can we predict an action that will do well in that particular task? So you can view it as this mapping, again, that takes as input some experience and the current state and outputs the action. And then the way that you learn this is a setting where you have a set of data sets, and each data set contains experience collected for each of the tasks. Okay, so this is kind of one way that we can view the meta-reinforcement learning problem. And then a core part of this problem, of course, is to design what this procedure looks like and how we're going to optimize this procedure. And then also something that's different than the standard meta-supervised learning problem is collecting appropriate data. How do we decide, now that we're in this reinforcement learning setting, we get to control the data collection process. So we need to figure out how we should collect this data, how we should collect kind of rollouts from our policy, and also how we should collect kind of our meta training data as well. This first part where we want to figure out how to collect data, this is kind of the problem of learning how to explore for a task, because collecting this data is exploring for that task in a way that allows you to solve that task. And so this part is what we're going to focus on in the next lecture on Monday. Today, we're just going to think about designing these learning procedures and optimizing them with reinforcement learning. Okay. So as a kind of instantiating example for this, in meta-reinforcement learning, let's say the different tasks correspond to navigating different mazes. So ultimately what we'd like to be able to do is, given a small amount of experience in a new maze that we haven't seen before, can we learn how to solve that maze essentially and allow us to navigate to the goal position in that maze. So in particular, what this is showing some trajectories in the maze where you're exploring the maze and so forth. And then given this experience in the maze, if you're then kind of reinstantiated at this point, you want your policy to be able to directly go to the goal and directly navigate that maze. So this is kind of the equivalent few-shot learning problem in a reinforcement learning setting. It's few-shot reinforcement learning. This is what we want to be able to accomplish at meta test time. And the way that we can go about accomplishing this is by training on lots of other mazes or lots of other tasks. So we can learn how to quickly explore and navigate a number of different mazes so that when we're then given a new maze at meta test time, we can quickly solve it. Any questions on how this works?
So the data for each task, there would be multiple trajectories from that task, or one episode, or is it multiple episodes or one episode from each task?
Yeah, that's a good question. So there's two different variants of the meta-reinforcement learning problem. One I'll refer to as the episodic variant, where you basically have K trajectories that you're trying to learn from. And one I'll call the online variant, which your data now just contains K time steps within that task. So you can consider either of these or something in between, basically. But yeah, you're either trying to learn from a small amount of kind of time steps or a small amount of trajectories. In both cases, it's a small amount of experience. Different problem formulations will consider different variants of the problem.
Okay, thanks.
There's also a question in the chat that's asking, when we fit a model to measure the reward, what is the reward? Is it the policy or the reward of the policy? So a Q function will be estimating the cumulative reward of a certain policy. So this is given by QPy, for example. Then something like a model-based approach will be learning to predict the next state and also the reward for that current state action and next state. So it kind of depends on the problem setting or on the approach. Okay, so that's the meta-RL problem. Next, we'll talk about black box approaches if there aren't any more questions on the problem. Okay. So for black box meta-RL approaches, we can basically translate all the ideas that we had for black box meta-learning to this reinforcement learning setting, where we're going to be training a neural network to take as input a data set, as well as your current state, and output the next action. Now, one of the things we talked about in black box meta-learning is that typically when you have some data, detrain, there's no kind of natural ordering of that data set. So there's kind of, you may want to kind of process that data in a permutation invariant way. But in reinforcement learning, the data does actually have temporal structure. So one very common approach for processing this data is to use some sort of recurrent network that processes the data sequentially. And specifically what this looks like is basically you roll out this recurrent network. Everything up until the current time step is basically the training data for that task. This is, and this training data includes states, actions, and rewards. And you basically pass in that data as it becomes available. So once you take action A1, for example, from state S1, then you actually, after you take that action, you observe the reward and also the next state. So you pass in that next state and that reward that you just received as input to your recurrent policy and predict the next action. Okay. Now, one question for you is, how is this approach different from simply just running reinforcement learning using a recurrent policy? And feel free to answer in chat or by raising your hand. And specifically, I have at least two things in mind with regard to how this general algorithm is a little bit different than if just running reinforcement learning with a recurrent policy. Any thoughts on how it is different? So there's a few answers in the chat. Said we don't use the predicted actions as the detrain is fixed. I'm not quite sure what you're suggesting. Said each time step is not dependent on the previous state, but all previous steps. So this is pretty close to one of the things that I was going to suggest. Suggest that the reward can be different from test time. So this is one of the differences, is that you're actually going to be training this recurrent policy across multiple different MDPs with different reward functions. And this reward function is kind of passed as input to the policy, which is a bit different than how you would typically use a recurrent policy. And then I guess getting to what was saying about each time step not being dependent just on the previous state, but all previous steps. The other core thing that's different about this policy is that the hidden state of your recurrent neural network is actually maintained across episodes within a task. So typically, if you were to train a recurrent policy, you would just kind of roll out that recurrent network throughout that episode. And then when you start a new episode, you restart the hidden state. But in this case, because we want to learn across multiple episodes, we want to actually kind of maintain what we've learned across those episodes rather than completely resetting the hidden state. So what this looks like is, say that we kind of have episodes of length capital T, then we're going to be rolling out this policy for T time steps right here. Then keep on maintaining this hidden state across the episode boundary, and we continue rolling out that policy to be able to learn across multiple episodes. So this is kind of episode 1, this is episode 2, and so forth. And then if you then want to start learning a new task, then that's kind of the only time when you'll reset the hidden state and start learning again for that new task. So it's asking, if you restart the hidden state, how does the model learn? So the model is able to learn like within a task. So you don't reset the hidden state within that task because it needs to be able to learn how to solve that task across episodes. You only reset the hidden state when you're trying to then learn a new task. So this would be like, I don't know, task I. This might be task J. This is asking, do we start with dtrain, or are we making a dtrain from the intermediate actions outputted by each model and constantly generating new trajectories from the model? So yeah, so the kind of the way that you can view this is we are constantly adding to dtrain, and at each time step, for example, when we're right at the beginning, when we're right here, dtrain just corresponds to S1, 0, A1, and R1. And then later on over here, dtrain corresponds to all of your experience so far throughout this trajectory. There are situations, well, I guess we'll get into this later, but there are situations where you may add to dtrain kind of incrementally. You just add one trajectory, then another trajectory, rather than adding them step by step. But for these approaches, you're basically adding to dtrain at every single time step. Okay. So concretely, this is sort of like what the model looks like. What the algorithm looks like is we sample a task. We then roll out this policy for n episodes, which is n episodes is the budget that we have to learn the task, incrementally adding to dtrain as we go. This would be under the dynamics and the reward for the tasks that we sampled. Then we potentially store that sequence of episodes in a replay buffer for this particular task. And then we update our policy to maximize the discounted return for all of the tasks in our replay buffer. And then you can kind of repeat this process. And note that when you're rolling out this policy, you're actually optimizing not just like for return after a fixed data set size, but you're optimizing for the return across the full learning process. So in many ways, you're optimizing actually for regret. You're optimizing for kind of not just for return after a fixed amount of data, but for return as you're exploring. And this allows you to optimize end to end, both for very efficient exploration and good exploitation of that data. And you're optimizing for kind of a good trade-off between exploration and exploitation. Okay, questions about how this algorithm works? Good question. So someone's asking, what does a rollout mean? This is actually a term that I didn't quite understand when I was learning things. So by rollout, I just mean a trajectory. So it's basically a way to say that you are kind of rolling out the policy, or you're incrementally selecting actions from the policy, executing that action in the environment, and so forth. So it basically just corresponds to a trajectory that is acquired by executing a certain policy. Okay, so you can also think of this as like execute, for example. Execute the policy for n episodes, you get some trajectory, and you store that trajectory of episodes in your replay buffer. Yeah, and then asking, what is it like for meta testing? At meta testing, you're given a new task, and you can basically just it basically just corresponds to these first two steps here, where you're given a task and you just roll out or execute the policy that you have, where you're incrementally adding to your training data. asking, how does this algorithm encourage exploration? So I guess there's a few different points here. So there's exploration at the meta level and also exploration within a task. One way that it will encourage exploration within a task is that, say, for example, say, for example, you're in the maze environment that we had before, and you get a reward if you go here, and you start right here, and maybe there are some walls and so forth that make it kind of non-trivial to get to the reward. Actually, should remove that last one. And so this is going to encourage exploration because if, for example, different tasks have rewards in different positions, so maybe this one looks like this maze looks something like this, then in different tasks, in order for this policy to get rewards within a task, it needs to be able to execute actions that allow it to identify where the rewards are. And this policy at the top can basically encapsulate both the exploration process and the process of actually exploiting that. And this recurrent policy won't actually be successful at getting good rewards unless it has actually sufficiently explored its environment to find where the rewards are. There's also exploration at the meta level as well. And you need to actually be able to kind of find a good strategy for learning and find a good strategy for finding rewards. That sort of exploration at the meta level really comes down to the objective that you're using for updating the policy. And here kind of standard approaches for exploration can be used to try to incentivize different kinds of approaches. So is asking, why can't we use this algorithm for standard RL as well? This algorithm written out here requires that you have multiple different tasks. I guess in principle, you could also apply this to a single task where you're optimizing for a good trade-off between exploration and exploitation for that single task. However, if you just do it for a single task, then through this process, you'll learn a good strategy for the task and you'll learn a good way to exploit and get lots of rewards for that task. And then if you're given kind of at meta test time given the same task, then it doesn't make sense to explore again for that same task because you've already learned a good strategy for solving that task. Okay. So one thing I want to touch on is how do you actually instantiate this algorithm with different architectures and optimizers? I'll highlight a few common approaches. So one common approach is to use some sort of RNN-like architecture like we were just talking about. And this might include things like an LSTM or a GRU. And then again, you're kind of rolling this out across episodes. And then the way that you could optimize this recurrent policy might be with something like trust region policy optimization, which is a policy gradient method, or A3C, which is asynchronous advantage actor critic, I believe. The takeaway here is that both of these approaches are on policy approaches and kind of are updating this policy with the latest experience that it collected. And this was summarized by these two works right here, which were two of the works that used some of the kind of the first works that showed with modern deep neural networks and deep reinforcement learning algorithms that you can learn how to learn for things like navigation tasks and other tasks. Also, the first author of the second paper, Jane Wong, is going to be giving a guest lecture in a couple weeks, and she'll be talking about a kind of a cognitive science perspective on meta reinforcement learning. So this is kind of a basic approach that you could use. One paper followed up on these, and instead of using an RNN architecture, they use a architecture that uses attention. It actually interleaved attention and 1D convolutions. I included this as an example of an architecture for the meta-supervised learning problem as well. And this paper actually showed results for both meta-supervised learning and meta-reinforcement learning. this is before things like transformers existed, but you could also use things like transformers and other like attention-based architectures to integrate your previous experience. And then the last example that I'll mention is this architecture right here. The way that this architecture looks is that it's actually a feed-forward architecture where it passes transitions into a single feed-forward neural network and then integrates those to produce a single context Z, or a single kind of embedding Z based on this context here. And then this embedding of the task is passed to the Q function in the policy, and they use a Q-learning-like method, in particular a method called soft actor critic, to optimize for the tasks. And this method is off policy in the sense that they're able to store data in a replay buffer and recall those experiences to train the policy in the Q function. Okay, you might ask, well, why would you use a feed-forward architecture if there's all this kind of temporal structure? One thing that is nice about this feed-forward architecture is that it is a lot more efficient because it's really easy to parallelize feed-forward calls to a neural network, whereas with a recurrent neural network, you have to process the data sequentially, which ends up being computationally a lot slower. Okay. So now that we've introduced the algorithm in different kinds of architectures, I wanted to go through a couple different examples of how these algorithms have been applied. So the first is the maze navigation example that I mentioned. And also, before I go there, there's a kind of a quick clarification on the previous one. That's asking the subscripts are episodes in the bottom diagram of slide 19. So in this case, these subscripts are actually corresponding to transitions. They sampled a number of different transitions. These transitions may come from different episodes, or some of them may come from the same episode. You can either use an online variant or an episodic variant. Okay, so for the maze navigation setting that I introduced previously, this is basically exactly the experiment that a couple papers have looked at, including this paper called A Simple Neural Attentive Metalearner. And what they did is they did meta training on 1,000 different small mazes, where they were trying to learn how to quickly navigate in all of these different mazes. And then they tested on held out small mazes and held out large mazes, with the goal of seeing if it can learn to navigate in these new mazes with a very small amount of experience in those mazes. And the results look something like this. So this is after the meta training process. So what it's doing here is exploring the maze to figure out where the goal is. So this is the first episode at meta test time. And it finds where the goal is. And then in the second episode at meta test time, it's able to go directly to the goal. So it's kind of, yeah, learned how to explore in a single episode. And then after that episode, it can exploit that strategy to go directly to the goal. Here's another example in a larger maze. And actually, to clarify, the policy only gets this first person viewpoint as input, not the right, but the right is useful for visualization purposes. Here's the first episode of meta training time, or at meta test time, where it's exploring. And then after that exploration episode, it's able to go directly to the goal. Cool. And then they also had some quantitative results where they compared this architecture that uses attention and convolutions to an architecture that uses an LSTM. And here they're looking at the average time to find the goal within each of the two episodes. So, and then this up here is just showing like a random policy. And first you can see that the time to find the goal decreases from episode 1 to episode 2, which suggests that it's able to learn from episode 1 to more quickly find the goal. And second, they find that this kind of attention-based architecture is better able to learn from data than an LSTM. There's also a question in the chat that's asking, can we speed up the learning of the goal with some heuristics? In general, you could imagine having adding some heuristics to the process. However, it's a little bit tricky to do that in these visual navigation settings. It's easy to do that if, for example, you had this low dimensional representation of your current state. But if you only have the visual observations, then it's a bit tricky to try to process those observations and provide heuristics because you don't actually know your kind of low dimensional 2D position in the maze. That said, you may be able to kind of shape the reward function in some way or something to make the meta training process faster or something else. Asking, what is the reward like? The distance at each point and the time from the goal. So the reward in this case corresponded to, I believe it was kind of a sparse reward where you received a positive reward when you were at the goal position, and either 0 or a small negative reward if you're not at the goal position. And this makes exploration really important. If it's something more like the negative distance to the goal, then you don't necessarily need to, it doesn't require as sophisticated of an exploration strategy because you can somewhat greedily act with respect to that. However, of course, even greedy approaches may not work because there's also walls and distances may not capture things like walls. Okay. Cool, so this is the first example for these maze navigation tasks. A second example of tasks is based on these continuous control problems that correspond to these simulated robots. So there's this half cheetah robot, this humanoid robot, this quadruped, and this 2D walker that is basically a bipedal robot that has 2 legs. And different tasks correspond to moving in different directions, running at different velocities, and also being able to handle different physical dynamics, like different friction and so forth. And one of the things that this paper in particular wanted to study is that meta-reinforcement learning algorithms are extremely efficient at learning new tasks, but the meta-training process may not be that efficient. Basically, the process of learning how to learn on all the meta-training tasks may require a lot of data. So kind of one question is, would you expect an off-policy meta-RL algorithm to be more or less efficient than an on-policy meta-RL algorithm? And recall that an off-policy meta-RL algorithm is able to store and reuse data, whereas an on-policy meta-RL algorithm basically just uses only the data from the current policy. So you can answer it in chat or raise your hand if you want. Do you think off policy is more or less efficient than on policy meta-RL? Cool. So at least a few people are paying attention. And people are saying that it'll be more efficient. To answer the question, I mean the amount of data that's needed for meta learning. So yeah, and so the reason why off-policy meta-RL is going to be more efficient is because basically off-policy algorithms can store data in a replay buffer and keep on leveraging that data, whereas on-policy algorithms, they need to collect new data every time your policy or your meta policy changes. And if you need to collect data every time your meta policy changes, then you're not able to reuse any of your previous data, and you have to just keep on collecting data each time you want to update your meta policy. Okay, and so here are what some of the results look like. So to unpack this, the x-axis is showing the amount of meta training data. So the amount of data needed for the meta training process. And the y-axis is showing the average return after adapting to one of the tasks in the task distribution. And in particular, what these different methods correspond to is Perl is an off-policy meta-RL algorithm that uses kind of the feed-forward architecture that I showed before. RL squared is using TRPO, and so it's an on-policy algorithm. And then these optimization-based methods are also on-policy algorithms. And you see a pretty huge gain by using an off-policy meta-RL method. So you're able to learn much more efficiently. These dashed lines are showing the final performance of these three methods. So we also actually see a performance gain in this case. But the main takeaway here is that they're significantly more efficient than on-policy methods. Okay, and then is asking, is hindsight experience replay necessary to make off-policy more efficient than on-policy? So in this case, there actually isn't any relabeling or experience replay or hindsight experience replay. There is, you are using a replay buffer, which uses experience replay. And experience replay is like something that existed a lot long before hindsight experience replay. If you don't use a replay buffer and don't replay experiences, then off-policy methods won't be more efficient than on-policy. They'll both be operating in this kind of on-policy setting. Okay, so those are a couple examples for black box meta-RL methods. One quick digression, kind of in relation to multitask policies, is that it's common to do like this sort of multitask RL where you have some information about the task that corresponds to like stacking, where to stack a Lego block or in what direction to walk. And in this meta-RL setting, in some ways you can kind of view this experience as some context that tells you what the task is. And then the last part of it as your policy. Essentially, this is kind of, you can view data as another way to express information or identifiers about the task. We also talked about goal condition policies before in goal conditioned RL. And in that setting, the task identifier corresponds to different goals. And I guess in this way, you can view meta-RL as a strict generalization of goal conditioned RL, because rewards can express things other than goal-reaching tasks. Although, of course, you can also apply it to goal-reaching tasks as well. And then the other way to kind of view this difference between meta-RL and goal-conditioned RL is that the meta-RL objective, your goal is to adapt to new tasks versus generalizing to new goals. So it's kind of the difference between K-shot learning to new tasks and zero-shot generalization to a new task given kind of a low-dimensional identifier of that task. Okay, so to summarize black box meta-RL, these approaches are very general and expressive. There's a variety of design choices for the architecture. The kind of downside from before is that these architectures can be hard to optimize because they have to figure out how to process experience and use that to learn the task. So they have a pretty hefty task to do. And then lastly, these methods inherit the sample complexity of the outer RL optimizer. If you use an off-policy RL optimizer that's able to reuse data, then they tend to be a lot more efficient than if you use an on-policy RL optimizer. Okay. Cool. Any questions before we move on to optimization-based meta-RL methods?
I was wondering if there are any scaling problems related to how long you unroll the policy, like how long the trajectory is.
Yeah, so if you're trying to learn from kind of a long trajectory, then the learning problem gets harder, certainly. And especially if you want to, if your task involves exploring in very sophisticated ways, then it also becomes a lot harder. And we'll talk about the exploration part in the next lecture. One way to kind of mitigate long horizons for very long kind of sequences that you're trying to learn from is to use something like an attention-based architecture rather than an RNN. Attention-based architectures basically allow you to shortcut. I guess basically these connections between the orange dots, they basically kind of shortcut the provide shortcuts across time that directly connect things in the far past to the present. And that allows you to handle potentially some of the optimization challenges associated with very long horizon learning.
That makes sense. Thank you.
And then it's asking, why is auth policy more efficient if you store more data? So the key thing is that by storing data and then kind of reusing that data, your model gets to take multiple gradient steps on a batch of data. Whereas in on-policy methods, you're not storing any data. You're not actually able to reuse data and learn from it. You basically can just take one gradient step on any batch of data that you have, and you have to kind of keep on throwing away data every time you change your policy. And as you might imagine, throwing away data leads to kind of pretty inefficient learning. Okay, so let's talk a bit about optimization-based meta-RL methods. So recall with optimization-based meta-learning, we're embedding this kind of optimization procedure or gradient descent into the learning process. Now, to turn this into a meta-RL method, the key thing that's going to change is that we're going to be running an optimization on experience from our policy. And instead of outputting some label, we're going to be outputting an action from our policy. One thing that's pretty different about these optimization-based meta-RL methods is they tend to, well, I guess we'll see examples of both, but they tend to lie more in the episodic variant, where you first collect a few trajectories, a few full trajectories, use those full trajectories to update your policy, and then roll out your adapted policy. Now, one question that I have for you again is, what should we use for this inner optimization? And you can answer this in chat or by raising your hand. Basically, we have three options. We could use policy gradients, we could use Q-learning, or we could use model-based RL. Does anyone have thoughts on or suggestions on which of these might be a good idea and why we might consider using that in the inner loop of a optimization-based meta-RL method? Also, there's no right answer here, so there's pros and cons to all of them. So is suggesting maybe model-based. Do you have kind of thoughts on why model-based might be a good idea?
Because model-based can allow you to have like off-policy learning, and like we discussed before, that off-policy can be efficient because it helps you to store the experience.
Yeah, so one kind of benefit of a model-based RL approach is that it allows you to use off-policy data, which allows you to be more data efficient. Other thoughts? Suggesting policy gradients because then we only need a few steps in the inner loop. So this is a good suggestion because maybe we would need kind of only a few steps. And suggesting Q-learning could work for large state spaces. Suggesting model-based because it takes into account change in the transition probabilities. Cool, so these are some good thoughts. So I guess I'll start with policy gradients. So policy gradients are nice because it's gradient based, and we know that you can kind of basically with kind of the policy gradient looks something like the sum over time steps of log pi times sum over time steps of RT. And basically just with just like one or a few gradient steps, you actually get a lot of information about the entire trajectory, which is nice. Now, one of the downsides of policy gradients is that they're on policy, so they can be pretty inefficient. Another downside is that policy gradients tend to be pretty noisy. And in particular, one thing you might notice here is that with this kind of form of the policy gradient, if the reward function is sparse or not very informative, then this policy gradient isn't going to tell you that much about the dynamics or that much about the task. So say, for example, you're in the maze, kind of in a maze setting, and you start off right here, the goal is right here, and maybe you have some trajectories that look, one trajectory looks like this, another trajectory looks like this, and another trajectory looks like this. From these three trajectories, you should have a pretty good idea of like where the reward is now, because you've basically exhausted all of the kind of paths where it isn't. And so from these three trajectories, you'd love to be able to kind of then figure out that the next thing you should do is go over here. However, if you have only these three trajectories, the sum of your rewards is 0 because you haven't experienced where the reward is. And so this policy gradient term is going to be 0 also. And so just because of this term being zero, right? And so if you're in the setting where you have very sparse rewards and you haven't yet experienced where the task is, you're not going to get any update to your policy, even though you just had all this rich information about parts of the environment where the reward isn't. So this is kind of one of the challenges with kind of policy gradients, is that they're noisy and they're often kind of uninformative. Asking, can't that be somewhat alleviated by attaching a small negative reward to every action? Yes, so it can be somewhat alleviated by that. If your reward function is instead kind of assigning like a small negative value to these things, or if you have some sort of baseline that suggests that you should be able to do better than 0, then that will allow it to push your policy in the right direction. This is kind of one extreme example too. Even if you have rewards that are like small negative values, for example, that still doesn't tell you, this gradient is still fairly kind of deprived of information about what the environment looks like and what the dynamics look like and so forth. Okay, so that's policy gradients. What about Q-learning? So one of the benefits of Q-learning is that it's off policy, and so it's very efficient at learning. The downside, which I think that may have been alluding to, is that because Q-learning is running dynamic programming, it requires many gradient steps. So if you look at the Bellman equation, for example, maybe I'll write it over here. Your Bellman equation looks something like Q hat minus R plus gamma max A prime of Q of S prime A prime. And this right here, this is kind of Q hat of S comma A. And basically each gradient step that you take on this objective, you're only propagating information one time step from S prime to S. And so as a result, if you want to propagate information throughout your entire horizon, then you need at least kind of H gradient steps to really propagate that information. And this is a big challenge for optimization-based meta-learning methods, where we typically run only a few gradient steps in the inner loop. All right, so this is one of the challenges with Q-learning. And then with model-based RL, it's both off policy, like was mentioned. It's also gradient-based. Model learning just directly corresponds to supervised learning. So this makes it also pretty easy to combine with optimization-based meta-learning. So both of these are quite nice. There are scenarios where model-based RL is difficult because like learning a model is hard, but in settings where model-based RL works well, we would also expect optimization-based meta-RL to be a pretty good option. Okay, so here are just some of the general trade-offs in terms of combining different kinds of optimizations with optimization-based meta-learning. Now let's go into a few examples, and in particular, we're going to look at an example of MAML with policy gradients and MAML with model-based RL. There actually aren't really any papers that look at something directly like MAML with Q-learning because of this challenge right here. There are a couple papers that suggest kind of different alternatives for potentially alleviating this, but they're really they're challenging, I guess. If you're interested in kind of looking more into this, one paper that you could look at is by Eric Mitchell et al. It's called, well, the name of the method is called Macaw, not quite a kind of mammal, but close. And it's using a kind of advantage-weighted actor-critic algorithm and combining that with mammal. Okay, so let's look at a couple examples. So if we combine mammal with policy gradients, this will just be like a really simple example. Like I mentioned before, combining mammal with policy gradients has some challenges. And this is actually just the example that was in the original mammal paper that illustrates one of the things that you can do with it. And in particular, we'll have just two different tasks here. One task will be just kind of going left, and the other task will correspond to going right. And first, we'll visualize what the policy parameters look like after the meta-learning process, but before adapting to one of the tasks. So this looks like something like this, where essentially the policy is running in place. It's kind of ready to run in one of the two directions. And then if we take one gradient step with respect to the task of running backward, we get a policy that looks like this. And if we take one gradient step with respect to the task of running forward, we get a policy that looks like this. So this is an illustration of how with policy gradients, I think these are with 20 trajectories used to compute the policy gradient, you can actually get a pretty drastic change in performance, which is nice. And these are both with shaped reward functions, which make it a little bit easier to handle the noise in the policy gradient. Okay, and then let's look at one more example with mammal plus a model-based RL approach. And in this case, we're actually going to be looking at the online variant of meta-RL, where our data corresponds to k different time steps from some policy. And so what this will look like is at meta test time, we're going to be adapting the parameters of our model to the last k time steps. And this will be with regard to the error of kind of f of SA minus the true next state. So we're basically going to be running gradient descent on this objective to update our model. And then once we compute our updated model for that current time step, we then plan a sequence of actions using our adapted model. And this will be kind of with respect to some task reward, which may be different for different tasks. And then at meta training time, we're actually going to be in a scenario where the task may actually vary within an episode even, but we're going to assume that the dynamics, for example, are constant within kind of a short period of time, but then it may change within a longer episode. And essentially, different tasks are going to correspond to different windows in time, where this kind of window right here will correspond to what we're wanting to adapt to, which is the last k time steps. And then this window right here, which is kind of the next h time steps, will correspond to our test set. And we can construct many different tasks by essentially sampling a point in time and sampling these kind of train set and test set windows. And this is assuming that the tasks are kind of, the tasks only change, or the dynamics only change sparsely in time, but it's still fine if, it's still kind of reasonable if, for example, the dynamics change here. You're only going to have a few tasks that are sampled with the task changing in the middle of it. And most of the windows will be kind of at different points in time where you have a consistent task. Like maybe this corresponds to like running on grass, and this corresponds to running on asphalt. Then we're going to have different dynamics for these two different parts of the environment. And when we sample tasks that correspond like right to this boundary, those tasks are going to be pretty noisy because we're going to be trying to adapt to asphalt when we're given data from grass. But everywhere else, when we sample all of these windows, we'll get kind of valid parts of a single task. Okay, so in terms of the algorithm, we basically sample these train sets and test sets from different windows of time. We use MAML to adapt our dynamics model on the train set, evaluate it on the test set, and then update the initial parameters such that that adaptation was successful. Okay, so how does this actually look like in practice? So we can look at some environments that are, as I mentioned before, dynamically changing in time. And if we first start with just a single model-based RL approach, where we're trying to fit a single model to with dynamics that maybe actually be varying across time, this isn't very successful. So in this first example, one of the legs becomes crippled, and a single model isn't able to capture the dynamics of a normal leg and a crippled leg. In the second example, these different panels have different buoyancy, kind of like if you're on a dock, and a single model struggles to capture the dynamics when you're walking on these different parts of a dock. And so the agent ends up kind of flipping over and is unable to kind of get to the goal, which is kind of over here, basically. Now, instead, if we use MAML with model-based RL, like I mentioned before, what these can do is they can actually adapt online to the latest K time steps and continuously replan using the adapted dynamics model to successfully make it over to the right-hand side of the screen. So basically here, at every time step, the model is being adapted with a gradient step, and then we're running planning with regard to that adapted model. Now, one of the cool things that was mentioned before is that model-based RL methods are really efficient, right? Because they can use lots of off-policy data. And so if you compare these approaches shown in green, these are both kind of model-based RL approaches, where this dark green approach corresponds to kind of MAML plus model-based RL. This approach here corresponds to basically an RNN-based MetaLearner plus model-based RL. Both of these are like much more efficient than these model-free approaches shown in red and yellow. And that means that it's actually potentially practical to run these on a real robot. So you can collect data on different terrains with this little six-legged robot. These robots are actually built by hand, and their dynamics vary significantly across different terrains and across different conditions of the environment. You can collect data like this, meta-train your model on these different windows of time, and then evaluate how well it can handle new situations. So in this first case, the goal is to walk up this narrow slope, and the goal is to be able to like walk along a straight line. If you just train a single model across all the different terrains and so forth, that model struggles to capture the different situations, including this test situation, and the robot ends up veering off to the right. Whereas if you kind of continuously adapt your model to the different situations, it's able to figure out a good model for this sloped terrain and follow it in a straight line. Then kind of one more example, you can take off like the front right leg of the robot. Again, the model that was trained across all the different terrains struggles to handle this situation, understandably. But if you adapt your model to kind of the previous windows of time, it can actually adapt to this new condition and walk in a straight line. It's asking, how do we figure out if the terrain has changed? Do we have a fixed horizon, we plan and then replan again? So in all of these experiments, it's actually resetting to the initial model parameters and adapting the model at every single time step. So it's just assuming that the model might have changed at every single time step. And with that adapted model, it's also replanning at every single time step. Because these models are kind of because the state is relatively low dimensional and the model is kind of just a couple layer neural network, it's pretty fast to run a gradient step. And therefore it's feasible to run this replanning in real time. If you had like a much larger model, then it may be a lot more expensive. Asking where is the reward signal coming from at meta test time. So in the case of the simulated experiments, the goal was just to move as far to the right as possible. So I think the reward function was something like negative, it may have been something like actually forward velocity, for example. In this case, there are actually motion capture markers on the robot that allow the robot to know where in the room it is. And then the reward function corresponds to basically like a negative distance to some waypoint, which may be at the end of the line. Okay, and it's asking, are we training at test time? So in this case, the model is kind of being adapted at test time with like one gradient step to go from f theta to f phi t. And this kind of happens with a single gradient step on kind of the model error on kind of the last k time steps. This is the only training that we're doing though. Okay, cool. Yeah, and this should be detrained because this is kind of what we're adapting to at meta test time. So this is the training set at meta test time. Okay, so to summarize, black box methods are general and expressive. There's a variety of design choices. They're hard to optimize in the meta-RL setting, as well as, of course, in the original meta-learning setting. In the meta-RL setting, optimization-based meta-RL methods have the inductive bias of optimization built in. They're easy to combine with policy gradients and model-based methods, with the caveats that I mentioned about policy gradients before, of policy gradients being very noisy. They are also hard to combine with value-based RL methods because you have to run a lot of gradient steps in the inner loop to get signal across your horizon. So these are very similar pros and cons to before, with kind of some added challenges if you want to apply optimization-based meta-RL methods. And then both of them inherit the sample efficiency of the outer RL optimizer. If you use a model-based approach, it's extremely efficient. You use an offline approach, it's a lot more efficient than a fully on-policy approach. And the efficiency isn't necessarily, it's kind of more dominated by this outer RL optimizer than the meta-RL approach itself. Okay, so that's it. So kind of we got through the lecture goals, and hopefully that gave you a decent understanding of the meta-RL problem statement and the basics of black box and optimization-based meta-RL algorithms. As I mentioned before, next time we'll be talking about how we learn how to explore. So in all of the examples we gave before, we had relatively shaped rewards. It was relatively easy to figure out how to adapt to the task. Or we were able to learn exploration strategies end to end in the navigation example. And on Monday, we'll talk about situations where we need to explore in much more sophisticated ways in order to solve the tasks. And then on next Wednesday, Karol will be talking about a Bayesian perspective on meta-RL and how we can derive some of these algorithms from kind of first principles from probabilistic graphical models. Cool, and then after that, we'll be talking about more advanced topics like hierarchical RL, lifelong learning, and we'll also have a guest lecture from Jane Wong, who will be talking about a cognitive science perspective on meta-learning.
Hello, I have a question regarding the optimization-based meta-RL.
Mm-hmm.
And can we go back 2 steps? I guess 2 slides. Yes.
Yep.
So say if for the optimization based, if your inner optimization horizon is pretty long, that means you have to perform multiple, even many gradient steps in your inner loop. And how does that affect your gradient with respect to the outer loop in terms of noise and also computation?
Yeah, so for if you have a very long horizon, like a very long episode, for example, if you have a value-based RL method, you need to take many gradient steps. But if you have a policy gradient method, you don't necessarily need to take a large number of gradient steps because the policy gradient is able to capture kind of information about the entire trajectory. Because like we mentioned, it looks something like grad log pi times the sum of rewards. So this contains a kind of information about the full trajectory. So in this case, it's actually fine to take one or a few gradient steps, even for long episodes. But for value-based RL methods, it's a big challenge, and very few methods have been able to kind of overcome this challenge.
Okay, and one more clarification is just for the manual structure in general, regardless if it's RL or ML, is generally not a good idea to take many steps in the inner loop. Is that correct?
I think the main downside is that it tends to be more computationally expensive to take a large number of inner gradient steps because then you have to backpropagate through that path. If you have enough compute, then it's not too much of an issue. And yeah, if you have a lot, plenty of compute, that is not a huge issue. You can also run into challenges though where you're basically the same kind of challenges when you train RNNs, where you get exploding gradients or vanishing gradients. That can also be a challenge, although usually the computational bottlenecks are more of a challenge than the gradient.
Okay.
Gradients.
Hi, I have a quick question. We have the example we covered snail in the maze example. That's very similar to the algorithm we implemented in homework 1, right? I was wondering how that's exactly meta-RL and how it's different from conventional RL.
Yeah, so it is. It's basically very similar to the approach that you implemented before. The key difference from kind of standard RL is that you are training it across multiple MDPs, and the hidden state is maintained across episodes within a task. And so you're allowing the algorithm to kind of learn across these episodes. Yeah, that's kind of the main gist of it.
Okay, and I have one more quick question, maybe two. So how is, sorry, I have zero RL background. How is model-based RL different from policy gradient?
Yeah, so model-based RL algorithms are, so policy gradient, you get basically the way that you update your policy is with something like grad log pi times sum of the rewards. And then with a model-based method, so this is, you just kind of directly update your policy. With a model-based method, like we talked about in the lecture on Monday, you train a neural network to model your dynamics and potentially your reward. And then you use this learned model to update your policy or to plan actions.
And what is inductive bias? And I think it was slide 36 or something.
Yeah, I guess what I meant by that is just you're building in kind of the structure of gradient descent inside the optimizer, rather than just completely training an RNN from scratch to learn completely without any kind of structure of learning or optimization.
And one more thing, you had something called zero shot. Going back, I was wondering if a K shot was a zero shot. I was wondering if you knew what that was.
Yeah, so what I meant by that is that basically when you're given when you're trying to learn from experience, you're kind of trying to learn from K data points. And so you're doing K shot learning, where K is greater than 0. And then in goal conditioned RL, when you're just trying to generalize to new things, you're given a task identifier that describes something about the task, like the goal that you're trying to reach, and you're not given any data. And so in that sense, kind of, you can view K as being equal to 0, and you're giving it information like the goal. And that's why it's referred to as like zero-shot generalization, because you're not given any experience, but you're still trying to generalize to a new task.
Thank you.
Yeah, so one question is about, is it usual to incorporate important sampling when you try to do meta-RL?
I guess there's a few different parts that you could imagine using importance sampling. If you're using policy gradients, that's kind of a reasonable approach to try to allow it to use off-policy data to some degree. So one paper that does something like this is called Guided Meta Policy Search, that use kind of importance weights in the outer loop to allow kind of a policy gradient method to use a little bit of off-policy data. I don't know of other approaches that do it in the meta-learning literature.
Sure. And also, in the Powell paper, the efficient of policy meta-RL paper, during meta test time, you don't update the policy, but only infer the, I guess, the context, which is like a task identifier, right?
Yep.
So what's the reason behind not updating the policy during meta test time?
Yeah, so it can be viewed just like another black box meta-RL method, where you're basically just kind of taking data as input. So all of this data here is referred to as C in the paper, but you can view this as dtrain. And we're taking dtrain as input and producing some kind of low-dimensional embedding of dtrain that corresponds to Z. And this Z is passed into the policy in the Q function. And so you can view this Z as kind of allowing it to take in data and adapt to that data.
Okay. If that's the case, wouldn't it be more helpful to separate the inference of the environment and the task goal? Like you try to, for example, if you have a different state space for each task, then you have to, like, if you want to have them to share some common structure, then you will have to, like, use a part of the goal state as like a reduced dimension of the goal space. I mean, the state base to incorporate information from different tasks and use an additional environment identifier.
Yeah, so if your MDPs are varying in different ways, then you could imagine potentially having like one encoder that tries to like summarize information about like the dynamics, and then like one thing that tries to summarize information about the reward, and then you could pass like both of those into these.
Okay.
The Pearl paper didn't do anything like this, and I don't know of any papers that does this, but it does seem like something like this could be helpful, especially if you know that some tasks share a reward function but just have different dynamics, and other tasks like only share dynamic, like have other tasks share the reward but have different dynamics.
Yeah, cool. So just one last question, and it's about the memorization paper. So in the loop of, I mean, when you calculate the generalization error bound within each task, that one is upper bounded by the generalization error of the meta parameter.
Mm-hmm.
And would it make sense to use that? Actually, use the, for example, Cal divergence between the updated task-specific parameter and the prior to determine the learning rate and that kind of stuff.
Right. So let's see. So I guess to write things out, maybe just pick a random slide. The what that bound is looking at is it's looking at basically like the generalization error it's saying that this generalization error is bounded by, or yeah.
I'm referring,
Plus,
I'm referring to the cal bound. Yeah.
Yeah, it's like something like this. This is from memory, but something like Q of theta times by P of theta. And then there's some other stuff over here. And you're basically saying that if this KL is
no, that's two part of the equation there. Like, you bound generalization error to the expected task error, and the expected task error is also bounded by the empirical error. And like I'm saying, if you can separate those two bounds and use the cal you're written on the slide to bound the meta test, the meta parameter, but the other cal bound to bound the updated parameter, like in the way you update it in the loop of member, for example.
Yeah, potentially. Maybe if you could post a question on Piazza, I think I may be able to give a better response.
Sure. Thank you.
Yep.
It's like, so I'm still very confused about black box meta reinforcement learning methods. So, like, my understanding is just as how you explained it to the other classmate. So we give trajectories to this black box recurrent structure network, and it like outputs some identifiers or like some latent vectors, some latent variables that will be fed into a policy gradient or like whatever RL methods that for training. Is that what it is? Then like so we still need to like collect data when we train it with the RL methods, and if on policy we'll collect new data.
Yeah, exactly. So when I said rollout policy here, kind of what I meant is you collect data with the policy that you have.
Okay, gotcha. That makes sense. All right, thank you.
Okay.